So now is the time to start our session 3 of consensus protocol in blockchain by Marius. So Marius is joined the Ethereum Foundation in early 2020 while completing his master at the TU Darmstadt. Before that, he worked on payment and state channels and mining software. He currently focuses on bringing Ethereum from proof of work to proof of stake. So thank you so much, Marius, for your time and for joining us today. Really looking forward to your session. So over to you.
Thank you for having me. Yeah. You need to. Yeah. Perfect. I'm quickly gonna share my screen. All right. Yep. Here we go. Yes, today I'm going to talk about consensus protocols and use cases. I think that was the original title. I'm not that big on use cases, so this is going to be a bit at the end, where I like talk about some of the protocols, some of the stuff that's working really good in blockchain right now. That like the use cases that blockchain is used right now. There are of course several other use cases that would be pretty cool and that people are working on. But my focus was more on what's happening right now. A bit about me. My name is Marius. I started working in 2017 on mining software. I had in university, I had a course called Programming Massively Parallel Processors, which was about GPU programming. So for programming for graphics cards with CUDA. And I thought to myself, okay, this is like really interesting to me, but I want to see this in action. I want to see actual code written in the wild. So I looked on GitHub, and the first project I found was Ethereum mining software, ETHminer back then. And I went through their code. I saw that they used some old API calls that are not really used anymore, shouldn't be used, are deprecated. So I went and started fixing it and started using the new API calls. And I quickly became part of the core team of ETHminer, became part of like a maintainer for this open source project. And then I joined I tried to create a startup with two professors of mine in the layer 2 space. We worked on payment and state channels. Basically, the idea is to compress many transactions into one transaction in order to make the blockchain more scalable. Because every time we send a transaction over the blockchain, the transaction has to be sent to everyone. Everyone has to validate this transaction, and this is of course pretty costly in terms of like computation and transaction fees and everything. And payment and state channels, also rollups, are ways to compress these transactions. And after 2.5 years at the startup, I wanted to finish my master's, so I wrote my bachelor's also on payment and state channels, and I was still at the university, and I wanted to finish my master degree. So I left the startup, and because in the last, so I put in like 1 month of notice or something, and in the last month I just, because we worked a lot with the Go Ethereum code base, I upstreamed some of the changes that I made or that we made internally to Go Ethereum. And then after I left the startup 2 weeks later, I got an email from the Ethereum Foundation whether I want to join them. And so I joined the Ethereum Foundation in 2020, and I'm currently working on Go Ethereum. Go Ethereum is the node implementation of Ethereum. So basically the software that takes care of maintaining the network, the software that validates the transactions, the software that also like creates the blocks that are mined and everything like this. I am part of the Ethereum Foundation. Everything that I'm going to say today is not like really is my own opinion and not the opinion of my employer, definitely. And I'm also not trying to get anyone invested in cryptocurrencies. I'm not trying to get anyone invested in Ethereum. I'm just really excited about the technology, and I think more people and especially more women should join the space because it's like really interesting. This was the thing that dragged me into this space from the beginning. It's really interesting software, and you can, like with small changes, you can increase the efficiency hugely. So if we, like back when I was doing mining software, I made some changes that made the software 2-3% faster, and this was like enough because the software was downloaded 5 million times a month or something. This was like huge speed improvements. And so this is why I'm in Ethereum and in core development. So a bit about core development. Core development is basically, that's what the core developers do. They work on the core of a blockchain. So the software that does basically everything, and it's the lower layer. So you build, it's the software that executes the smart contracts. It's the software that sends and verifies the transactions. And it's a great mix of different fields because you have things about economics, you have things about cryptography, networking, you have all these like different fields of computer science mixed together in a really interesting way. You always have to think about, is this secure? How can this be gamed? How can like maybe people grieve other people by DDoSing them or whatever? And another thing that's really interesting is you build something that users actually use and that other companies are built upon. This means you need to really think about what's your API going to be? What's the developer experience going to be? Are people understanding the documentation that you write? Are people getting the ideas that you like how to use your protocol, how to use your node? And a big part of core development is also deciding on the future of the protocol. So with Bitcoin, it's a bit different. The idea behind Bitcoin is that it's not easy to change it. They actually never really changed it. And so Ethereum and most other cryptocurrencies, I think there's no way to build a currency like Bitcoin now, because you have all these other cryptocurrencies that can do way more. And so cryptocurrencies or the software behind it, it has to change, it has to evolve. And the big idea behind blockchain is, of course, we don't want to have a single point of failure. We don't want to have a single team, a single person deciding on it. And so one big problem is, how can we do this in a decentralized way? And this is part of core development. It's also the part that's most exhausting, because you always have to, you are kind of a public figure, at least in the space. So you have to talk to other people, you have to discuss with them, you have to find a consensus on what to do next, and which features to build, which features to ignore. And so this, I think this is the part that that stresses me the most. The development part it's not easy, but I think it's manageable for like most people. And this part, deciding on the future, it's pretty difficult. So yeah, what is core development? What is in a node? So I'm working on Go Ethereum, also called Geth, and we have different things. So we have the chain, which is like the blockchain from the beginning. So the first block is called the Genesis block, and then you build blocks on top of that. You can see that on the top left. And we have the EVM, which executes the smart contracts. So smart contracts are like small programs that you can deploy on this distributed network. And you send a transaction with a smart contract code, and you can invoke functions on the smart contracts. There will be, I think, the next or the session after that will be around smart contract development. It's usually done in Solidity, so that's the high level language, and this Solidity gets compiled down to EVM bytecode, and the EVM is the actual stack machine that executes the smart contract. We have the miner, or the part that comes to consensus. I'm going to explain a bit later about why we need this and how it works. We have Dev P2P, which is our networking protocol. So the idea is a lot of people run nodes, and you don't usually want to run a central node, but you want these people to actually find other nodes, connect to them, send messages to them, and see and like create this network without having to have these central authorities within the network. Then we have the transaction pool. So we usually make the distinction between mempool and transaction pool. Maybe some of you have already heard about the mempool. The idea is the mempool is all of the transactions that are currently in the network. So if you send a transaction, it needs to be valid for the transaction. It needs to be included in a block. But before that, the transaction needs to be sent to all the people. It needs to be verified. It needs to be put into a block by the miner, and then it is valid. And the transaction pool is what we locally use to store all of these transactions. If we mine and we are chosen to create a block, we take transactions out of the transaction pool, create a block out of it, and append it to the chain. And the mempool is like the global view of all floating transactions in the network that are not yet validated, and the transaction pool is what we locally have in our software. Then we have things like the historical state. Basically, so we have the blocks, but we also have the state, and these are two different things. Basically, the state is the accounts of everyone, the contract code, and the contract code of all smart contracts, and storage for every contract. So you want to be able to, for example, store some piece of data in your smart contract. This is also part of the historical of the state, and you can recreate the state, the current state, by executing all blocks from Genesis. And the historical state, so we maintain the current state, and we might also maintain historical state, parts of the historical state. I'm going to explain it a bit later, a bit better. And then we have things like the JSON RPC API that people can talk to. So other programs can do things like query for a block. So which transaction were in block 10? or they can query for a transaction. Transaction XYZ, was it executed successfully or not? And these things are like surfaced to the user in the JSON RPC API. So let's start a bit with the consensus algorithm. Why do we need a consensus algorithm? The idea is we have a network. So in this example, I have a network of 5 people. There are some balances on the network. If it really interests you, I can explain a bit how these balances came to be later. But let's assume for the first time that these balances were established somehow. We have a state of the network, and now we want to mutate the state. We want to do some state transitions. So the alien wants to send 2 euros to the sunglasses. And so what do? We take the balance of the alien, which was 10 minus 2, and we increase the balance of sunglasses plus 2. And this is the transaction. The transaction gets stored in a block, so on the right side. And now that's pretty easy. The question now comes: what happens if the sunglasses wants to send 5 euros to this anonymous emoji, or 5 euros and 5 euros to the ghost emoji, but it only has 9 euros. So one of these transactions, we have 2 transactions that are they cannot be executed. They cannot be both executed. One of them has to be rejected. One of them has to fail. One of them has to be executed. And so we have to establish an ordering. And this is basically what the consensus algorithm does. It establishes orderings between transactions. So what can we do? We can just take a vote. We are 5 people. We can say, okay, 3 people say the first transaction should go first, and 2 people say the second transaction should go first. The problem with this is that in an online system, in a software system, you can create identities out of thin air. So that the alien could say, hey, I'm not 1 guy, I'm actually 3 guys. And there's no way for the others to verify whether he's actually 1 guy, or if these other anonymous identities are one or the other. So the alien could take over the vote and say, hey, I always want this transaction to go first. And it's even worse than only the ordering of transactions, but you can also rewrite the history. If you have more than 51% of the network for a vote, you can rewrite the history. So the idea behind proof of work is that we don't vote with our identity, but instead we have a computer, and we vote by solving small puzzles. And if we actually solve the puzzle, then we get to propose a new block. And everyone is solving these puzzles, and the one who solves the puzzle first, he gets to propose the new block, and so on. And this means, and the idea behind it is, this hash rate, or these computers, they cannot work on 2 different problems at the same time. They can always only work on 1 problem. So you cannot fake it. You cannot say, hey, I'm actually 10 people, even though I'm only 1 person, because you can always verify how much hash rate there is, or that this person actually solved the puzzle. And the big idea, the core assumption behind it is that more than 50% of the hash rate is honest. So the honest chain will always outgrow the dishonest chains. So, and the idea behind it is, so that there are different ideas. The Sybil resistance and proof of work is actually a Sybil resistance mechanism. So like Sybils is or creating Sybils is creating fake identities, and the other idea is the fork choice. So this is this actually, the fork choice rule is actually the thing that is that does the consensus, not the proof of work. But this is like really, like, most people say the proof of work is the consensus algorithm. It's not really true. Proof of work is the Sybil resistance mechanism, and the fork choice rule is the consensus algorithm. But yeah, so it's just like really minute details. The idea is, here on the right side we have a chain. This is the genesis block, the block 0, and there's a block built on top, and there's a block built on top. And now we have 2 different blocks built on this second block. We have 3A and we have 3B. And now we, as a miner, have to decide, are we going to build our block on 3A, or are we going to build our block on 3B? Which of those chains should we pick? In Bitcoin, it's pretty easy. You will always pick the heaviest chain. So you will first verify that both of these chains are actually correct, and all of the out of all of the correct chains, you will always pick the heaviest. So the one where the most work was done. The problem with this is that all the energy, so if we say, okay, 3A or 3B was a bit earlier than 3A, so 3B is a bit heavier, then we will build on 3B, which means that the energy on 3A is wasted. And Bitcoin needs longer block times for the networks to stabilize, because they have to do this. In Ethereum, in the current Ethereum network, we use Ghost, which stands for Greedy Heaviest Observed Subtree. And in Ghost, we can include this block into our canonical chain. The transactions in this uncle block are not going to be validated or anything, but we can get the we can include the energy that was wasted on this block, because our chain also gets heavier if we include this block as a miner. And inclusion of this block rewards us, and it also rewards the miner that actually produced this block. So like in the case of like two, so there are 2 miners that produce blocks almost at the same time, and these blocks are distributed to the network, and now the network has to decide between those 2 blocks. And in Bitcoin, it is like the better block gets picked and the other block is wasted. And in Ethereum, one block is picked and the other one can be included as an uncle. And this is pretty good, because it allows us to have faster block times. So the time between blocks can be sped up. Yeah, so these consensus protocols, they've gone through like they were proposed pretty early. Leslie Lamport did a lot of work on the on consensus protocols. He formulated all the problems that consensus protocols should solve, and he also proposed some of the solutions. So BFT, Byzantine fault tolerance, is also name for a protocol, but also the name for the problem. And this was introduced by him. Then we have practical Byzantine fault tolerance protocols. And the cool thing there is you have finalization. This is basically previously, or in Bitcoin or Ethereum in proof of work chains, you can never be sure that your transaction will be valid, or if once your transaction is mined, you can be sure, okay, this is valid, but you can never be sure that there isn't some other chain which is way heavier, which will be published at some point, which will overtake the normal chain and will exclude your transaction. So you have no finality. You always have like a minuscule chance that your transaction will get reverted in the future, and this is of course bad. That it's a property of proof of work, but this is of course not great. I'm seeing some questions about Ghost. What type of data structure is Ghost based on? Well, Ghost is based on the blockchain. So there's not really a data structure. It's Ghost is just the mechanism on how to pick these blocks, and well, there's not really a data structure that well, you can say the data structure is a block tree. So you have this whole thing is a directed acyclic graph. You have a root, and then you have edges, and it's a graph or a tree. The other question, which miner gets the reward? Both miners get the reward. So if I build a block on top of 3B, so if I build block 4 on top of 3B, and I include 3A as an uncle, 3B already got his block reward. 3A gets an uncle reward, which is less than the full block reward, and I get my block reward plus also a reward for including this block. It's not the full block reward for 3A, but they get a bit of money. So yeah, then there are some more protocols evolving. The cool thing about Bitcoin and crypto or in cryptocurrencies is that it accelerated a lot of research and work in this cryptography space. There's a lot of money coming into a space that didn't really have money before, and so there's a lot of new research and new work done in the last couple of years. So Raft and Tendermint. So Raft is only fault tolerant. So there's a difference between Byzantine fault tolerance and only fault tolerance. One thing is tolerant against malicious nodes, and the other thing is tolerant against crashes. So if a node goes down in the network, then the network will still continue. That's fault tolerance. We have Tendermint. Then we have some leaderless consensus protocols. These are, so the idea behind IOTA and Hashgraph is that in order to create a transaction, you will always validate 2 previous transactions. And there's the idea, you either validate 2 random previous transactions, or you have to validate 1 transaction from you and 1 transaction from someone else. So 1 random transaction and your previous transactions. And the idea is that after a while, the network will stabilize. The problem with it is that we don't have a shared world state. So we cannot really do smart contracts in the way we do it on EVM or on Ethereum chains, because you don't have the shared world state. It's possible to do, at least they claim it's possible to do smart contracts, and I think it's possible, but it's not possible to write them in the easy way that we use it in Ethereum-based chains. Then we have things like the tower consensus, where you have a proof of history, a verifiable delay function. Basically, the idea behind a verifiable delay function is you can verify that there was a delay. So it's not easy to explain it. The idea is you will compute something, and only for example, you will hash a nonce over and over and over and over again, hash the same thing over and over and over again, and you can be sure that your hashing of the nonce is the so other people can only verify this by also doing the computation, and there's no shortcut. And so this can be used to establish a global source of time, like that you cannot influence. And yeah, it's not easy to explain this. Sorry, I can give some more details if you guys want to. I'll just put it in chat. And then we started with the Casper FFG consensus. This is the consensus that we are going to use in the new Ethereum, in Ethereum proof of stake. And the idea behind it, like it uses these BLS signatures, which are really nice. I'm going to talk a bit about BLS later on. So the idea behind proof of stake is in proof of work, you tie identity indirectly to money. So the more miners you can buy, the more miners you can run, the more hardware you can buy, the more you can vote in this network, the more stake you have in the network. So it's indirectly tied to money. But we can also directly tie it to money, and this is the idea behind proof of stake. So the idea is everyone who wants to participate has to lock some money. And now there's some random process, and we say, okay, out of all the people that deposited their money, we are going to pick at random some, and these are the people that can produce new blocks. And for producing a block, they will get the block reward, and others will verify the block and also attest to it. So they say, I've seen this block, I think it's valid, here's my signature on it. And if they sign something that is invalid, then they will lose some money. And the core assumption behind proof of stake is that more than 66% of the stake is honest. So Ethereum actually launched the beacon chain in December 2021. Yeah. No, 2020. I don't remember. So a year ago, and this chain runs, but it basically votes on empty blocks. So there's no state there. And what we want to do in the future is merge the current proof of work chain and the proof of stake chain together. And yeah, so we have these two other consensus protocols, Aura and Click. The idea behind Aura is you have finality, and the idea behind Click is you don't have finality. So the idea behind Aura is someone proposes a block, sends this block to everyone, and everyone has to send their attestation. So they have to say, yes, I accepted this block, and they have to send this to all the other participants in the network. And in Click, someone just proposes the block and sends them to the others, and the next one has to build on top of this block. I'm not really going to talk about Click because Click has so many problems. One of the problems is that you can just DDoS the block proposers, and then the network's not going to run anymore and everything, and you don't have this acceptance state and everything. So the thing about Aura, it's this block acceptance stage has a really huge overhead. You have to send network messages to everyone in the network, and every node has to send network messages to everyone. So we have like a factor of n squared network messages, and this is O of n squared. It's not really n squared, it's n times n minus 1 divided by 2. But yeah, so the problem with these algorithms is they usually scale up to 30 to 40 validators. But we want to have a decentralized network. We want everyone to be able to propose blocks, to participate in the consensus, because otherwise there's just a too high chance of these people getting corrupted, either by state or whatever, and not including certain transactions, so censoring the users. And yeah, so that's what we want to prevent. And so the idea behind Casper FFG, this is the new consensus algorithm that will be, or that's currently being rolled out with Ethereum's proof of stake, is so you have Casper FFG, the friendly finality gadget, and LMD Ghost. I knew what LMD stood for, but I forgot already. So the idea behind this, you have you vote for blocks, and you also so someone creates a block. So the block creator is picked out of at random, and you vote. He creates this block, and other people have to attest to the block. So they say, okay, this block is valid, and that's basically the same idea as with Aura on the left side. But the cool thing is we have BLS signatures now, and the cool idea about BLS signatures is you can take two signatures from two people and combine them. Yeah, so LMD stands for last message driven, greedy, heaviest observed subtree. So Ghost is the greedy, heaviest observed subtree, and LMD stands for last message driven. Sorry, the BLS signatures. The idea behind BLS signatures is if I have a signature from person A and I have a signature from person B, I can combine these signatures, which will result in a signature that is valid for the combinations of the signatures of A and B's public keys. I have a picture for that in a moment. So the idea behind Casper FFG is you vote on the blocks. If someone votes on two conflicting blocks, so for example, if someone votes on 3A and also votes on 3B, then you can get slashed, which means you lose your deposit. You have to deposit 32 ETH currently, and if you do something wrong, then you get slashed. And if more than 2/3 of all people have voted on an epoch, so an epoch is 64 blocks. If more than 2/3 of people voted on 64 blocks, then this epoch is marked as justified. And if you have two consecutive epochs voted on by more than 2/3 of the votes, then you are finalizing. And so you also have two. Basically, the idea is you have two different periods. You have the periods, the period where the chain can move, and this is the first 128 blocks. And after that, you have a period where the chain cannot change anymore. So the early chain is like proof of work, where you can have reorgs where like blocks can be dropped if another chain overtakes it in votes. But after two epochs, you are sure that this is the chain that most of the people agreed on, and it's finalized. Which is like this is some new property that we have in proof of stake that we didn't have in proof of work. One question that came in about the properties of proof of stake is some say that proof of stake leads to centralization. The more stake, the more control. Is that partly true? And how is decentralization guaranteed? Yes, it's true. More stake you have, the more control you have. But it's better than proof of work. Because in proof of work, people just assume that like because you can vote with your computer, it's super decentralized, but it's not, because you cannot actually vote with your computer anymore. You have to if you want a chance of really being part of the vote, you have to invest huge amounts of money into mining hardware. Even if you like, I'm not sure how it is, but like if you want to you have to invest millions of dollars into having like 10% of the network or something. And a lot of companies are doing that. And the problem is, you have, so if I want to create 10, if I want to deposit 10 validators in ETH, I have to deposit 32 Ether per validator times 10. So there's not much room for improvement for me. If I buy one graphic card, I have to pay the normal price. If I'm going to buy 10 million graphics cards or 100,000 or something like this, then I'm going to get a way lower price. So you have huge economies of scale in proof of work that you don't have in proof of stake. And it's a property of all blockchains that the people that are producing the blocks will accumulate, like over the long term, will accumulate money, but they also have to pay expenses, and they also want to do stuff with their money, so the money will also be distributed. And decentralization is not guaranteed in any project. You cannot guarantee it. The thing why I really want to do it, I really want to have this switch from proof of work to proof of stake, is the energy consumption. So recently I gave a talk about this where I stole this slide from. There's a lot of like talk about the energy needed by proof of work, and the energy consumption by proof of work, and it's the energy consumption of NFTs or of simple transactions. So the energy consumption of, like, you cannot really say this transaction costs that much energy. That's not really how it works. You can amortize the energy by transaction. It gives us an insight, but it doesn't really show the whole story. And so the energy consumption of proof of work in Ethereum is 24 terawatt hours per year. This is roughly comparable to the energy consumption of Ireland. The thing is, energy consumption is one issue, but it's not the worst thing, because a lot of energy that is used by proof of work mining is actually renewable energies. So, for example, in Iceland, there are a lot of geothermal power plants that produce excess energy, and this energy can be used for mining. So the CO2 emissions of Ethereum are around 7 megatons per year, which is a lot, but it's not as bad as like other sectors. So compared to the energy usage, the CO2 emissions are actually not that bad. But if we can get rid of the energy usage, we can also get rid of the CO2 assumptions. And this dormant energy can be used for other things. For example, like charging your electric car, or producing hydrogen for power plants or whatever. And yeah, so right now we use roughly 20,000 tons of CO2 per day in Ethereum, and that's really a lot. And this is why I really push for this move from proof of work to proof of stake. And in the future, we'll hope to use as much energy as like a small city, a small like a bigger town, 2,000 households, and not like real countries. Yes. So this like the left side is the slide that I wanted to show you on BLS. Basically, the idea is you have these signatures from 3 different people, and you can combine it, and you get a shared signature that you can verify was created by all of these 3 people. So you don't have to send these 3 signatures individually, but you can send the shared signature, and you also have to send the indices of which people actually signed the signature. And on the right side, this is so the process of moving Ethereum from proof of stake to from proof of work to proof of stake is called the merge. And the idea is we have these 2 networks. This proof of stake network that was started in December 2020, and the Ethereum chain, which has been going since 2015. And the Ethereum chain contains the all of the state, so the history and the state, the balances of all the people, the smart contracts, the smart contract code, everything. And it is like the blocks are produced under proof of work. And what we want to do at the merge is switch that out. So we still have the history, but we create the new blocks with the new mechanism. Yeah, so I still want to go a bit into core development. I also want to show you a bit of code, because I think it's women who code, so we should at least see some code today. And yeah, so I wanted to show you all of these components in the code. So we have so Go Ethereum. The thing behind so Go Ethereum is the node software that I'm also working on, and lots and lots of chains have actually took our code and made some changes to it and launched a new chain. So for example, the Binance Smart Chain is a one-to-one copy of this code base, or the Avalanche has some parts taken from Go Ethereum, because Go Ethereum it's open source software, and people can take it, modify it, and use it for their ideas. So I think it's nice to give an overview of Go Ethereum, because if you maybe somehow end up in some project that uses Go Ethereum, then you already have a head start. Go Ethereum is written in Go, which is a pretty cool programming language. I know there's rules against like discriminating against people with different programming languages. I think Go is pretty cool. Yeah, so let's see. We have the miner, so we can take a look at the miner. The miner, basically, it creates the blocks. So the whole the real code is in the worker. It's a bit too complicated to explain it. Wait, I have to go here. It's easier to do it in my IDE. So yeah, we'll take a look at the miner, and so what we do is we create some. So if we get a request that we need to create a new block, then we generate a new block. So this is the that's not the, so this is the real. So we get the request, hey, please prepare a new block. So what we do is we create a work package, and we fill it with the transactions, and then we commit it. So we send it to the actual code that does the mining, and the mining finalizes and assembles the block. And once that's done, so this creates the block. And okay, it's not. I think it's not really working to explain this. But yeah, let's just move on. I can explain a bit about the Ethereum virtual machine. That's maybe easier to understand and to do live. So the idea is you have the Ethereum virtual machine, the EVM, most of you have probably already heard about it. And this is part of, oh yeah, we are at time. I'm sorry. I still have lots and lots of stuff to go through. I'll try to be a bit quicker now. So the Ethereum virtual machine executes the smart contracts. The contracts are deployed in transactions. You can, if you want to create a new smart contract, you send the code that you want to deploy together with the transaction, and the code gets deployed on the network, and you can interact with it. You can call functions on it, and execute stuff that you want to do. It's a stack-based machine. It's quasi-Turing complete. We have the notion of gas. So if we have a Turing complete machine, then we don't know if if a program will actually terminate because of the halting problem. So what we did is we have the notion of gas, which means that you have opcodes, so operations like push, store something in memory, store something in the storage, and each of those opcodes consumes gas. And you can send some gas with your transaction, and once this gas runs out, then your transaction gets reverted because you ran out of gas. If your transaction stops peacefully before you run out of gas, then the transaction works and the state is not reverted. And yeah, and then you have gas, and you have the gas price. The gas price is what you are willing to pay per unit of gas. So if you go to Etherscan or Gas Fee Now, you'll often see a gas price of 100 gwei or 20 gwei or something like this. And you have to multiply this number by the amount of gas that your transaction is going to use. If you have a complicated transaction, like I don't know, doing a token swap between two tokens, then you have to pay more gas. If you only send Ether, then you only have to pay 21,000 gas. And in the EVM, we also have pre-compiles. Those are more complex cryptographic instructions like EC recover for recovering ECDSA signatures, Blake 2F, which is a building block for all of the Blake hash functions, BN256 add, also BN256. So doing operations on the BN256 curve, stuff like this. And the thing that we are most worried about is the state of the network. So this is roughly a full node. A full node has all the blocks from the first block until the newest block. So this is the bodies. So you can see this snapshot was taken at block 13 million. We have all the bodies from the first one to the newest one, and we have the storage snapshot. This is the current. This is like everything that is stored in smart contracts, and this is all the balances of everyone on the Ethereum chain. And we have the trinodes, because we have right now we have the state in two different formats. We have it in the snapshot, which is a flat format, and we have it in a tree-based format, which is the state trie. And so this and this is actually the same data, just stored in different ways. And yeah, so this is a full node. It contains everything from the beginning plus the newest state. And we hope to get and the receipt list. This contains, for every transaction, we have over 1 billion transactions at the moment, I think. For every transaction, it contains things like sender, recipient, was this transaction successful? In which block was this transaction included? And logs. So you can create events. You can emit events in your Solidity smart contract, and these events are stored in the logs. And we have a Bloom filter for it, so you can do easy filtering. And it's really complicated, and no one really uses it. So we hope to get rid of it soon. Since we are, the Ethereum improvement proposals, we are already a bit over time. I'll just stop here. You can start asking questions. I'm happy to answer questions for the next 2 hours if you want to. Ethereum improvement proposals are basically what we use to coordinate the core devs to update the network. And I have a whole second talk about different use cases, but I'll stop it here. If you have questions about core development, I'm happy to answer anything. I hope I inspired some of you to take a deeper look into this. It's for me, it's really interesting. It's just super interesting software. You have all of these different components. You have different you have to be proficient in different parts of the stack. But you don't have to, but like you can find niches for you. So for example, I'm doing some work on the JSON RPC API. I'm doing some work in the core, but I'm not really doing some stuff on the dev P2P or the networking layer, because I really don't know how that works. I did have, one question that just came in is, how can you start with core development? And I have it here. So the way I started with core development was people came up to me and asked me whether I wanted to join the team, because I was doing a open source contributions to different protocols. And I think that's a great way. That's a great way to show the people in a project that you know your stuff, that you're interested in this project. Another great way to start getting into core development is actually as an EIP editor. So we really need those. Basically, EIPs are Ethereum improvement proposals. If you want to change something on the network, you can write down what you want to change, and other people will take a look at it, will most often criticize it, and we need those people, the people that criticize the people, and this is called EIP editing. So the EIP editors make sure that the EIP is sound, is like formatted correctly. You have some requirements that you have to do. If you're interested in something like this, you can go to eeps.ethereum.org, where we have like a list of all the EIPs. And so, for example, this EIP 214 introduces a new opcode, and so all of this work is done. All of this work is done in the EIP repository. So and we really need people to take over this work, and it's a great way to get started. You just start with so you have the pull request. You can just start with like reviewing them. Which we can take a look at some of mine. So this one creates a new specification for EVM traces. I have the whole like spec. I have it here, and the EIP editors, they will do stuff like, I don't know, say I have this comment, but they don't want this comment anymore, so please delete it. Or this section is optional, and we really need people to take over this work. And the other thing is testing. That's pretty near and dear to my heart because I'm doing a lot of testing, and it's a great way to get started. We have a few different ways to test. We have unit tests within Go Ethereum. We have a lot of reference tests. So if you want to create a new Ethereum implementation, so there are Ethereum implementations in different languages from different teams. We have Go Ethereum written in Go. We have Bisu written in Java. We have Nethermind written in .NET. We have Aragon written in Go. We have Acula written in Rust. We have Parity or Open Ethereum also written in Rust. We have Silkworm written in C++. And then we have some old C++ implementations. We have a Python implementation, a JavaScript implementation. And all of these implementations, they all have to do the same thing. They all have to implement the Ethereum protocol. And we have reference tests to make sure that these people all implement the same thing. And so this is also a great way to get into core development. Look at the reference test, look what is not tested there, and then write tests. It's not an easy workflow to do it, but I think it takes 1 or 2 days to get used to how to write a test, and then you can. And then there are a lot of people that are really nice and can get you there. We have fuzzing. Fuzzing and differential fuzzing. Fuzzing is basically hitting the program with random inputs until it breaks. And differential fuzzing is the idea is hitting two different implementations of the same thing with the same input and verify that they act correctly. And so this is, for example, what I did for my master thesis. I took 4 EVM implementations, and I wrote I created reference tests, let them execute on all of these implementations, collected the results, and verified that the results were the same. And then we have also a lot of test nets. So whenever updates to the clients itself, major releases happen every 2 or 3 weeks probably. But if we want to change the core protocol, we have to create the software. Then we have to tell everyone, hey, those are the changes that we want to make to the protocol. Do you agree with those changes? Do you think those changes are good? So for example, we had this EIP 1559 where like some people thought this EIP is not good or not really needed. Other people thought it was really, really good. And so there has to be a lot of discussion. There we have to, all of the core developers have to come to a consensus. And then we have to implement it, and then we have to start testnets. We have 3 or 4 long-running testnets: Gurley, Robson, Rinkeby, and Coven, Sepolia. So 4 or 5 longer running testnets. And then before we make those changes, we spin up small testnets just to test the changes before they go to mainnet. Yeah. There's another great question coming in after the merge and transition to proof of stake. Is Geth still needed and developed or developed? Yes. So the way it will look is I have another presentation about that. Let me quickly switch to that. This is the way it will look after the merge. You have the execution layer client. This is Geth, which will retain most of the functionality. So if we go back to this idea, the only thing that will change is that the miner will not be in Geth anymore. And Geth will retain the chain, we will retain the historical chain, we will retain all the capabilities that we have with JSON RPC and everything. But we will not make the fork choice. So we will not make the choice between 2 different forks anymore, but we will, the consensus layer client, this is the client that currently runs on the beacon chain. This client will tell us, this is the block, this is the newest block, please import it. And then we will import and execute it and say, okay, this block was not valid. And then the consensus layer will say, okay, we will not follow this chain. Or we will say, okay, this block is valid. And then the consensus layer will say, okay, we will follow this chain. And then if the consensus layer wants to create a new block, it will say to us, hey, Geth, please create me a new block with these parameters. And because we have the transactions, we have the state, we can execute the transactions, we can create the block and send it to the consensus layer, and then the consensus layer will actually send it to the network. There will be some things that will be different. So for example, we will not send the block to other people anymore. We will only, this will be done by the consensus layer. We will only send the transaction to other people, and we will also send the historical block, so everything that was in the past. But not if we create a block that we will send it to everyone. That's not happening anymore after the merge. Where does the validator client fit in? So the validator client, that follows the proof of stake chain. So we have this picture is basically this picture. So this picture on the right. The idea is you have the beacon chain, which does the proof of stake, and we have the proof of work chain. And at the merge point, the beacon chain will start including these blocks from the proof of work chain. The proof of the blocks, the execution layer, this is what's currently Geth, and the consensus layer on consensus layer clients is what will be the validate it's consensus layer client here. This will follow the beacon chain, and the validator. So the consensus layer client is actually split in 2 parts again. It's the consensus layer client, or the beacon chain client, and the validator. And the validator is actually only the small piece of software that signs blocks. So there's a question whether how this actually saves energy. And the idea is so this like splitting this up doesn't really save energy. The big energy saving is because we don't have to do this mining anymore. This mining is the really energy intensive part, because so the idea is for the proof of work, you solve these small puzzles, and these puzzles they get harder the more people are mining. And because it's very profitable to mine, there were times where a Bitcoin block would give you, I think, $200,000-$300,000. People started investing a lot of money into mining hardware, and it's basically an arms race. If I buy 10,000 GPUs, then I get a bigger share, and then other people will buy 10,000 GPUs. So my share will, like my share of the pie will be smaller. So I'm going to buy even more. And so we are in this we are with proof of work in this arms race situation. And this is what where all the power is spent. So the power is not really spent by maintaining the network or validating the transactions. It's only by figuring out who can propose the next block. And because it's really easy in proof of stake to say we're going to randomly choose someone. It's really easy to choose who can propose the next block. That's why we don't need that much money anymore. All right. Yeah, it's perfectly fine to end it right here. Thank you very much.
All right. Thank you so much, Marius, for your time. Yeah, thank you so much, Marius, for your time, and really appreciate for you to share on your knowledge with the entire blockchain community of Women Who Code. Thank you so much.
Thank you. Yeah, I'm also I'm going to be joining the mentoring program as a mentor. So if you're interested in that stuff, definitely check that out. And I'm also on the Slack. If you have any questions, I'm pretty busy during the day, but I'll often find like time to answer quick questions. So just find me, send me your questions or whatever you want to do, and yeah, I'm always happy to help.
Awesome. Thank you so much, Marius. And thank you to all the attendees also waiting up. So if you have any more questions, as Marius mentioned, you can reach out to him on Slack. And take care and stay safe during these COVID times. All right. Bye-bye. Take care.